everyone, we're going to construct a Cayley table for Z6 under addition modulo 6. Show that the Cayley table represents a group. Prove that the group is cyclic and write down all the generators and write down all the proper subgroups. So the first thing we have to do is construct a Cayley table under addition modulo 6. So, and we're with the integers. So we start with 0 and go 1, 2, 3, 4, 5. And then 0, 1, 2, 3, 4, 5. Now, addition modulo 6 is pretty easy. So basically, you're just adding this up. So this is going to be 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1 plus 1 is 2, 3, 4, 5. But 1 plus 5 is 6. So divide that by 6, and the remainder is 0. So you're back to 0. So the rest are the same way. And you fill that in. So addition modulo is a lot easier than multiplication. Okay, we have to show that it's a group. Well, the table is closed. We have no new elements, so it's closed. Table is closed. I don't know what that was. All right. The identity for addition is 0. 0 appears in every row and every column. 1, 2, 3. Oh, here's 1. 0 appears in every row and every column. That means every element has a unique inverse. In the group has a unique inverse. All right? And addition is associative. All right. Prove that the group is cyclic and write down all the generators. So the order of our group here is 6. So we need to find an element that has an order of 6. And the way you do that is you take the numbers, and I'm going to take 5. So if you take 5, and we're going to write 5 to the first power, that equals 5. And then 5 squared means 5 plus 5. Well, 5 plus 5 is 10. Divide that by 6, and the remainder is 4. So this is going to equal 4. 5 cubed is, in this case, would be 5 plus 5 plus 5, which is 15. And divide that by 12. The remainder is 3. And so forth. You'll come down here and get to 5 to the 6th equals 0, which equals your identity element. So since 6 matches our 6 here, that means the order of 5, order of element 5, equals 6. Now, so it equals the order of the group. These two have to match. Now, if 5 is a generator, so that means that generators of the group are 5 and its inverse. Because if A is a generator, so is A inverse. So the inverse of 5 is going to be 1. So you see the 0 here? There's 5, there's 1. You have a 0 here, and so that goes 5 and 1. So both of these are generators of the group. Now, if you want to check for other ones, you'd have to have like 4 to the 6th would have to equal 0, or 3 to the 6th would have to equal 0, and none of these will work. All right, the next question is write down all proper subgroups of this. So our order of our group is 6. So basically, for that, the order to be 6, that means we can have 1, 2, or 3 subgroups, the proper subgroups. Of course, this whole table is a subgroup, but it's just not a proper subgroup. So let's see how many we have. Do we have 1, 2, or 3? Because these are by Lagrange's theorem, these are the proper subgroups of 6. Is the factors of 6 are 1, 2, and 3. So I know that we have a group with the 0. So 0, 0, 0. That's closed. And it follows all the rules of a group. Another one would be plus 6, 0, 2, and 4. So 0, 2, and 4. 0, 2, 4. 4, 0. 0, 2. So the 0, 2, and 4. So this would be 0, 2, and 4. 2 and 4. And then here we have 4, 0, and 0, 4. It's closed. It has the identity element in it. Each element has its own inverse, and so forth. So that's a group. And another group we have is, let's see, plus 6, 0, and 3. So for 0, 3, we have 0, 3, and 3, 0. So in that case, this one would be 3, 3. So this would be 0, 3. And no, this one would be 3, 0. And 0 would be 0, 3. Well, I should put the 3 here. All right. So that's closed. This group is closed, and it follows all the restrictions we need for it to be a group. And that's it. Thank you. Have a nice day. Bye-bye.